Present.
All right. Thank you, Dr. Bronsberg, and hello, everyone. Welcome to this talk. It's entitled Machine Learning 101 for Healthcare. Before we get started, though, I need to get my thing to go. Okay, I need to basically state that I have basically no commercial interest. I'm not attempting to sell anything. I have no conflicts of interest, so I'm just here to present information. You'll see the outline is kind of long because this is a huge fail, but we're going to just kind of talk a little bit about some of these. We're going to start out with kind of a brief introduction, history and learning, and we'll talk about a few popular machine learning methods, KNearest Neighbors, neural networks, and deep learning. Then we'll talk about a few problems with it, and then I'll end up with a few examples from healthcare applications. So artificial intelligence has a pretty long history, basically in computer science, because shortly after electronic computers become available, people were thinking, well, how can we make them more intelligent, act more like, solve human type problems and stuff. It also has a fairly long history in healthcare, but it hasn't been really that successful in healthcare. And one of the big problems with that, it's not easy to understand how a particular AI model makes its decisions. And that's actually starting to change a little bit, although I'm not going to talk about it today. Later we'll be talking about neural networks and about the weights and stuff, how you adjust them. Once you have a trained model, it's really not easy to understand how it makes those decisions. But recently, people have started thinking about, well, those weights are just another data set, and they can use something called topological data analysis to try to get some insights from those weights, how it's actually making decisions. But unfortunately, we won't have time to talk about that any further today. Kind of the history of AI kind of comes back. It started back in the summer of '56, when a lot of top computer scientists at that time met at Dartmouth College to basically lay the foundations. They had a pretty high level of expectations at that time, but unfortunately those have not been met, and we're still working on trying to achieve their 1956 vision. Basically, here's one of the things from John McCarthy. Was a very famous computer scientist back there, very prominent. And in '55, he wrote a proposal for this conference, where they proposed a two-month 10-man study of artificial intelligence. And basically, their idea is they're going to try to find out how, at that point, how to make machines use language, form abstractions and concepts, solve kinds of problems reserved at that time for humans, and improve themselves. Well, as you can imagine, we're nowhere near all of that right now. So they were very, very over optimistic in what they thought they could accomplish in 2 months with 10 people. So basically, AI started out trying to use the formal logic and formal symbolism stuff, and they soon found that approach really didn't work very well at all. So at that time, they started thinking about the machine learning, based upon, the human brain and stuff, because, humans can learn and stuff. So the idea is, could they mimic to some extent what humans do? And you basically have machines learn. So machine learning is now the majority of work in the artificial intelligence field. So basically, the first of those, kind of machine learning was the perceptron, a simple neural network. And basically, it was able to do a few things, some things that the more, formal logic and stuff wasn't able to do. But it also showed its limitations pretty quickly and stuff. So about almost 10 years ago, basically the concept of deep learning was developed, and basically has really exploded in the AI field, including in healthcare AI. And the reason they basically took that long to get the so-called deep learning, where you have multiple layers and stuff, is basically limits due to computational power. There's been a lot of advances in computer hardware, computational power, and it wasn't until about 2010 or so that they actually got to the point where they had enough computational power readily available that they could start doing deep learning. And we'll talk about what deep learning is a little bit later. So here's essentially, if you look at the history, basically artificial intelligence started officially at '56, but up to about '80, it was pretty much based upon, formal logic and stuff. And then about 1980 or so, they developed machine learning, neural networks and stuff. And then finally, about 2010, 2012, they actually got to deep learning, which has led to an explosion, true explosion of work in machine learning and artificial intelligence. So as I said, basically, they started out using formal logic and symbols, but machine learning doesn't use that. Basically, it's a way of, when we talk about machine learning, it's a way to have basically present data to a technique, a model, and let it learn, hopefully learn from that data. And there's a whole bunch of different methods, K-nearest neighbors, neural networks, deep learning. We're going to talk about those in a little bit more detail later, but there's other things like support vector machines and stuff that we don't have time to talk about. But those three I mentioned are the ones you're likely to come across, are fairly common in healthcare. So as I said, we want our machines to learn from data, and that's not really different from how we as humans, we learn from experience. Essentially, experience is just a form of data that we learn from. And so the crucial features of human learning are essentially remembering. If you can't remember, then you're not going to learn anything. But you also need to adapt and generalize what you learned and stuff. So we also want to have those features as part of our machine learning process. So as I said, it's sometimes called sub-symbolic processing, since it doesn't use formal symbols or logic. And essentially, machine learning, it wants to make machines basically be able to, computers to adapt their behavior and become more and more accurate. So I should point out that it has basically, machine learning is based upon concepts from a number of different academic fields, including neuroscience, biology, statistics, mathematics, and physics. So you can see there's quite a bit to it. We also have to worry about the computational complexity of these algorithms, because sometimes they take a huge amount of time and memory to run. And essentially, computational complexity can be divided into two areas: complexity of training, which is frequently the big area that takes a lot of time, and then a complexity of applying the trained method, which generally isn't as bad. We're kind of used to working with our laptops and our desktops and stuff, and it seems like everything we do, if we do Word documents and stuff, things run pretty fast. But there's a lot of problems in science and mathematics and engineering and stuff, including in machine learning, where it takes a lot of time, a lot of memory, and a lot of time for something to happen. And that's the case, especially as we'll see later, for deep learning. So just don't feel that you're going to be able to train some model within a few seconds. Sometimes it can take days or longer, depending on how complex it is. One of the tasks that you have to realize that in most machine learning, not all, but most of them, is you have to decide, you have a number of variables, say, in a given data set, which of those variables are you going to actually use in training and using your model. It turns out that basically, frequently you'll do what's called feature selection or feature engineering, where you have so many variables you can't put all of them into the system, so you get rid of them. But the problem with that is that you may be engineering out important features that we don't realize that they're that important, but the computer could have identified had they been exposed to them. So, there's been a lot of different definitions of learning. We're not going to worry about it too much. We're just going to use a very loose definition, basically getting better at something through practice. So there's a few different types of machine learning methods. Supervised learning, which is the most common, unsupervised learning, reinforcement learning, and evolutionary learning. And certainly, most commonly used is supervised learning, and we'll define those briefly on the next slide. Basically, when you're doing supervised learning, your training set, what you're using to train the model with, has inputs, the variables. It also has the correct output. So basically, it tries to give an answer, then you tell it what the correct answer was, and it tries to adjust its parameters so that it will do better the next time. Unsupervised learning, basically, you don't have those correct responses, so you just give it the input data, the input variables, and it tries to break those up into categories and stuff. Essentially, and obviously that's maybe not quite as nice sometimes as supervised learning, but that happens. Sometimes you don't have the correct answers, and although we won't talk about it, for example, Cajon and self-organizing maps are one technique that's used very, very commonly for unsupervised learning. Reinforcement learning is essentially you tell the method you know what the correct answer is, but you don't give the correct answer to the model. You just tell it when it gets the answer wrong. You just say, yes, you're right, or no, you're wrong. But if it's wrong, you don't tell it what the correct answer should have been. And then there's also maybe somewhat less use evolutionary learning, using some that's basically the evolution that, kind of the idea of, evolution of biological systems. So, essentially, genetic algorithms would be a very common example of evolutionary learning. So what are the steps when you're going to do some sort of machine learning? Well, obviously, you got to collect and prepare the data. And don't underestimate the preparation phase. Sometimes that can actually take more time than the other steps combined. Actually getting your data prepared, because there's always, data's always dirty. You got to worry about, what am I doing about missing values? What about what's going to happen with, values that are wrong and things like that? And combining data from different data sets, things like that. It can actually take a lot of time and a lot of effort. Then you do, if you need to, feature selection or feature engineering, as I said, decide which of the variables you're going to use. And, you have to be very careful of that, or otherwise you'll engineer out what is the important factors. And so that'll lead to a bad result from your machine learning model. Then you decide what sort of machine learning algorithm do you want to use, whether it's neural networks or KNearest Neighbors or whatever. You select basically the parameters. You have to train it up, by exposing it to data and stuff. And then finally, you have to evaluate, how is your training model? Is it, your trained model, is it working sufficiently well for your particular application? So these algorithms require lots and lots of data, preferably without too much, errors and not too much noise. But that can be very difficult to get. And you have to realize, essentially, the larger your data set, that requires more computational cost. It takes longer to actually do the training. So the problem is, you might think, well, there's probably is an optimal point where I have a large enough data set, and then I could actually, that would give me the best training and stuff with the least amount of data. Well, unfortunately, finding that optimal spot is almost impossible. There's no good theory to do it. Generally, people have to work with it, kind of experiment as they go. Once again, feature selection is identifying what you think the features are, the variables that are most useful. It requires a prior knowledge of what you're working with. But once again, sometimes people don't have that good of understanding, or don't understand the problem and the data as well as they think, and they actually engineer out some of the important factors. I'll talk a little bit more about that later. So we're going to just briefly talk about 3 different types of machine learning methods, and these are ones that are commonly used. If you read the literature, you see what people are actually doing. These are 3 of the most common: K-nearest neighbors, neural networks, and deep learning. So starting with K-nearest neighbors, essentially what you do is you have some sort of data training set. And basically, the values for the variables, each of those, say, patients in that training set. And then what you do is, if you have a new point, we'll call it X sub Q. If you have a new point, basically, you look at the, how many, the K number of training points that are nearest to that new point. And then you assign basically the class based upon the maximum number of, which class has the maximum number of those points that are close. Essentially, K is actually, when you say K nearest neighbors, well, K is actually a very important parameter you have to worry about setting as part of this. But just to make this a little bit more concrete, suppose I have here basically some of the training set points are represented by 2 classes, pluses and minuses, and you see them scattered around the diagram here at the bottom. And then I actually, create a new data point. So a new data point comes in, we'll call it X sub Q. It's located right here. In this case, I set K equals to 5. So basically, I want to see which 5 points, training set points, are closest to this XQ. And they've actually been put in a circle here. And you'll see in this case, there are 3 of the negative training set points and 2 of the positive ones that are within that circle that are the closest. So in this case, you would actually assign the classification for X sub Q, the new point, you would set it to negative, because there are more negative points around it than positive points. You also might get into a situation, though, where you have an equal number. If you said, it's probably nice always to do odd numbers. Say if you have 2 classes, do odd numbers. And that way you never get into a situation where you have 2 basically equal numbers. So if you set k equals to 6, for example, you might get into a situation where you had 3 minuses and 3 plus, which can be a problem. You have to come up with some sort of way to handle that sort of situation. And that's why frequently you'll see that k numbers that are selected are odd. So once again, the choice of k, how do you make that stuff? Basically, it specifies how many of those nearest neighbors you're going to look at to try to classify a new point. So as a general rule that you should be aware of, as you increase the value of k from 1 to 3 to 5 to 9 to 19 and so on like that, the boundary between, say, classes becomes smoother. And I'll show you in the next slide an example of 2 different classes. But you also should be aware that in this technique, case nearest neighbors, that there's been a general kind of rule of thumb that's really become super popular. And that is, if you have n samples in your data set, say n patients in your data set, then a good choice of k is the square root of n. So if if it's basically, if you had 100 patients, the square root of 100 is 10. So they would say a good choice of k would be 10. Well, if that sometimes works, but sometimes that can get you into really serious trouble if you just blindly follow that general rule of thumb. And we'll see why here, I think, on the next slide. Basically here, they've actually done k-nearest neighbors calculations for different values. Basically, you see, this is a case where you have 2 classes. There are some of the points, say here on the left diagram, you see that are essentially red dots. Those are one class, and then they're blue dots, the second class. Well, but the problem is you see here kind of toward the boundary here, you see there's kind of, some of these blue dots, some of the red dots are intermixed. So it's going to be, that makes it hard to actually separate those out. But if you use k equals 1, the lowest value you could use, you can see it does not have a very smooth boundary here. Basically, it kind of has these fingers that go out and kind of little puddles of red area here are these red dots that are surrounded by blue. So it actually does a pretty darn good job of classifying all of those points, even though there's some intersection. If you look now over here at k equals 3, well, it's still doing a pretty good job, but not quite as good, because basically the boundary, between these two areas, between kind of the light red and the light blue, is becoming a little bit smoother. As you go here to k equals 5, it gets a little bit smoother. So now we're not doing nearly as well. And if you increase k again on the right hand side, you'll see once again it's not doing very well at all. You might say, well, when's a case you might have a situation like this? Well, one thing might be is if you had, for example, if you had some maybe pathologic ratings from cells that are either normal or cancer. And cancer is divided generally into 4 grades, 1 through 4, where grade 1 is, essentially fairly not that different from normal cells. And then grade 4 would be very, look very different under the light microscope. Well, in that case, you might actually have something maybe not quite as bad as this, but you'd have something closer to, what you're seeing here, basically with maybe some blue, they're kind of intermixed. Maybe that's the cancer that are intermixed with the normal cells and stuff. So to actually, you actually use that rule I said before, the square root of n, so if you had a million patients, you set k equals 1,000, and it would not work at all. It would get a horrible result. Whereas if you used k, a very small number, like you do here on the left, or even on the k equals 3 and stuff, you would get a much better classification. That contrasts basically here if you have a case where things are really well separated. Once again, maybe here, these red balls in the upper left, maybe those are all grade 4 cancer, and they look a lot different from the normal ones down here. So there's very good separation. In that case, it really doesn't matter much what k you use. If you had a million patients, if I use the square root rule and said, k equals to 1,000, I still get something that would look like this boundary here, and it'll work fine. But just be aware, you have to realize, that is basically as you increase k, this boundary becomes smoother and smoother. And if you have some overlap, like you did here in the previous, you're going to get worse and worse as k gets larger. Next, we're going to talk about neural networks. Essentially, neural networks are inspired by the human brain. What organism do we know that learns the best? Well, humans. So that's basically people started looking at what's known about the human brain, and they developed some sort of nodes that are connected in some sort of topology, which just means pattern in this case. And you have some sort of basically strength of interconnections between the nodes, which are specified by weights that are originally set up to random values, and then you expose the neural network to data that where the true value is, and basically you adjust those weights to try to make it do better. There's a large number, it's a fair number of different approaches to adjusting the weights, but certainly probably the most commonly, or one that's taught earliest, what's known as gradient descent, and we'll see that in just shortly. But remember, the nerve says there's picture here, painting on the bottom, supposed to represent kind of the cells in the brain, and they're basically interconnected into very complicated patterns, in the sense that basically you have like billions and billions of nerve cells, and each nerve cell can be connected maybe thousands of other cells. So it's an extremely complex pattern, and obviously in an artificial neural network you cannot you can't have billions and billions of them, of these nodes, and trillions of interconnections. But still, the idea is good. So here at the top, basically, is a kind of a representation of a biological neuron in the brain. Here on the left are the dendrites. These are what actually accept inputs from other cells. Down here, at the kind of the right end of the cell body, there's something that calls it's called the axon hillock, that basically, it sums up in both time and space these incoming signals. If it exceeds some threshold, then a signal goes down, called an action potential, down to the axon, which then basically makes connections with other cells. That's the output that goes into the input, the dendrites of other cells. And so the way that's simulated basically here in real life is you have maybe n inputs. There, a weighted sum of those are taken, and that basically is put into an activation function, which generates the output. And we'll see a little bit basically what we're talking about in more detail, and that generates your output. Why? And in general, there could be more than one output. This one only shows one for simplicity, but in general, you can have more than one output. So here's what a true neural network would look like. You would have here maybe 3 inputs, 1, 2, 3, from node 1, 2, 3. Each of those nodes is connected to a single node, one of the nodes in the hidden layer. And there's a single hidden layer, and you can see there's various weights here to connect for those connections. Those are initially set to random values. There's also what they call bias weights, basically to the hidden node, and also the output node, that also initially set to initially to random values, and are trained also. It's been found that these bias weights can actually improve the training performance. And then basically these say node A takes a weighted sum of these inputs, runs it through its activation function, and sends that to the output. And then basically the output node here, there's only one in this case, takes a weighted sum of those inputs it gets from the hidden layer, and runs that through its activation function, and then generates the output. So once again, the weights are initially set to random values, and you want to try to do something to change those weights so that basically you improve the performance of this neural network. But it's actually, you would say, well, I want to change those weights so that it gives the very theoretically best performance that network can do. Well, the truth is that basically, when you look at, as we'll see in another slide or two, you generate an error function to help you change those weights, and there's a lot of local minima in that. So what you want is the global minimum, the very best performance. But in fact, when you're doing this training, frequently you're going to get trapped in these local minimum, and then you have to decide, well, that's not the best, but is it good enough for the application I'm working on? So as I said, basically, that when at a given node, you're taking a weighted input, basically a weighted sum of the input. So here's what it would be from node A in that previous diagram that I showed you. Basically, here's coming in, it's weight 1A times the input A, plus weight 2A plus the input 2, plus the weight 3A times the input 3. That is, and then plus then the weight, those bias weights. That's what's the input that's coming in to node A here. Well, what they do is there's a number of different activation functions There's some like, hyperbolic tangent and softmax and things like that. We don't have time to talk about them. But what a very commonly used one is known as the sigmoid function. And I show it here at the bottom where, this number e is 2.718. So it's basically 1 divided by 1 plus e to the minus x, where x would actually be that weighted sum. And here's actually a graph of it. You'll see when x is 0, its value is 0.5. As x becomes larger and larger and larger, it approaches, it never quite reaches, but it approaches 1. And then as x becomes more and more negative, it actually approaches 0. And that basically makes sense from this. If I set x equal to 0 here, I've got 1 over 1 plus 1, which is 1/2. If I set x to be a very, very large positive number, then e to the minus x is going to be very small, and essentially you can have something close to 1 over 1. If x is a negative number, I'm going to have a large negative number. I have 1 plus 1 over 1 plus, then a very, very large number, which is going to be close to 0. Well, one of the advantages of using the sigmoid function is what else do you know from theory and stuff that runs between 0 and 1? And I'll tell you, it's probability theory. Basically, probabilities always run between 0 and 1. And that allows you to basically then to frequently interpret if you're using sigmoid functions, that the output of that network is a probability of something happening. To give you an example, maybe you basically collect some data on patients who are, admitted to an ICU, and essentially it will, basically a lot of variables at admission, and your output's going to be, did they live or die? Did they live to get out of the ICU, or did they die in the ICU? Well, you can actually, train a neural network by basically presenting all those variables and stuff. And if you use the sigmoid function, you're going to get an output of between 0 and 1, and that can give you, depending on how you train it, the probability that a patient, say, is going to die while they're in the ICU. It won't tell you absolutely, but give you an idea of which patients are more at risk of dying, and thereby probably may need even more intense care than what you're talking about. But kind of the key factor for a neural network is they generally have a single hidden layer, as I showed down here. They have 3 inputs, they have 4 nodes in the hidden layer. In this case, they have 2 outputs, and that's fine. Well, a single hidden layer for traditional neural networks. And now we're going to move on to deep learning. And basically, deep learning you can think of as essentially kind of a generalization of the neural network we just talked about, but instead of having one hidden layer, it has multiple hidden layers. So essentially what you're doing is you're doing some sort of, composing some sort of simple but non-linear transformations that basically, which allows you to represent information at higher levels the further along you get into the deeper network, the deep learning network. So essentially by composing such simple nonlinear functions, you can actually develop very complex relationships. As I said, higher levels will actually represent, basically aspects of the raw data that are more and more important. But one thing, you had to be aware of is that, when we talked about neural networks a couple of minutes ago, generally they can't take in all the data. You have to actually do feature engineering. You have to select out which features you're going to present to the neural network if you're working with a complex problem. That is not the case with deep learning. You can actually present all of the data. If you're actually working, say, with the chest X-ray, so you have essentially a 2x2 array of pixels, picture elements, or standard neural networks, you have to present only some sort of features from that. But for deep learning, you can actually present every single pixel to the deep learning network and let it decide what's important. All right, so this is consider a simple medical image, chest X-ray, which I just mentioned. As I said, it's a 2-dimensional array of pixels. So if you had 3 hidden layers in a deep learning network, this first layer might actually come to represent edges. Edges at some sort of locations and orientations within that film. The second layer might actually look at for particular arrangements of those edges. And then the third layer might assemble these motifs into larger combinations, maybe corresponding to real objects and stuff, parts that we're familiar with. To give you a simple example, this is not necessarily medical. This is where basically you present images, and there's either a car, person, or animal. So down here at the bottom, you actually put in, here you would actually put in the pixels from your two-dimensional picture. The first hidden layer might actually find the edges that are found in that. The second hidden layer might find corners and contours. Then the third layer might actually develop, come up to, give you some sort of objects and stuff. As you can see here on the left, it looks like we've got a tire there. Here in the middle, it looks like you're starting to see kind of a face and a chest and an arm and stuff. And then that output can then decide whether that's a car or a person or animal. But you can see there's a hierarchy of concepts that are developed. The further you get into the network, the higher, higher level of concepts that are developed. And that's the advantage, a big advantage of deep learning over standard neural networks. This is once again just kind of a representation when we talk about your traditional rule-based systems that are used, say, in clinical decision support, or basically have hand-designed programs, if then else type statements that come up with by experts for the output. Classic machine learning, the standard neural network here gives you your input, and you actually come up with whatever the humans think are the important features, and give us still a single hidden layer and then an output. Whereas, if you look at the far right with deep learning, what happens is you put in the original the raw input. It basically extracts simple features in the first hidden layer, then it does additional layers, hidden layers, then get more abstract features. And then finally, you can map those features to generate outputs. It gives you better results than you have with the classic machine learning. But always remember, people, there's been a lot of talk about machine learning, how cool it is, deep learning and all that. But even deep learning is just a simple chain of simple transformations. So that basically what it means is anything that requires reasoning, like long-term planning, data manipulation, programming, that sort of stuff, deep learning is not able to do. It can't do any of the higher intellectual functions. And like I said, generally deep, the fact for a deep neural network is they have multiple hidden layers. Here's an example that has, several input layers on the left. There are 3 hidden layers and then 4 nodes in the output layer. Another type of deep learning is called a convolutional network. And basically, it's used in a lot of things like that have two-dimensional structure, like images, chest x-rays, and speech, and things of that nature. And it's inspired by basically how neurons work in the visual cortex of the human, basically, which, and if you look at the human visual cortex, the individual neurons up there respond only to a restricted region of the visual field. They respond only to restricted region of the receptive field. And so and those receptive fields actually partially overlap. So that's what they do with these basically convolutional neural networks. And there are multiple hidden layers. There are generally of 3 types: convolutional, pooling, and fully connected layers. Convolutional ones are basically the ones that only look at part of the visual field, part of the field they're looking at, and then does some processing and passes it to the next layer. The pooling basically combines outputs from several convolutional neurons into a single layer in the next a single neuron in the next layer, and then fully connected are like the ones that we saw, with the traditional neural networks. So here's an example, and you can see, once again, we have some sort of input over here. It might be an image here on the left. Then there's a convolutional layer, and each one of those neurons only looks at some part of that input image, and then basically you can pool it. And then you might actually go with another convolutional layer, then another pooling layer, finally interconnected, and finally an output. So they can have very complicated architectures with lots and lots of ways, many, many different parameters. And even though what we're showing here in deep learning, I've shown you things like 3 or 4 different hidden layers. In practice, frequently people are using 400 or 500 hidden layers. So many, many, many hidden layers. So you can imagine how complex that would be. So, convolutional neural networks are great for working with like images and speech and time series like electrocardiographs and stuff, but they are not those. But basically, they're not good if you have sequential data. If you're talking about speech or some sort of time series, and basically they don't work that well. So they've actually developed another type of deep learning called recurrent neural networks. to handle such things as like time series. So basically, and these have at least one, that should be one instead of on, a feedback connection. In truth, they generally have many feedback connections, which allows you to deal with sequences and time series. And that allows whatever activation you get from a layer to flow around in that network. And it actually could be set up so it has a memory. But they're actually very powerful. You know, they have a couple of ones, they have these distributed hidden layers that you can actually store information from the past very efficiently. You also have nonlinear dynamics so that you can update these hidden nodes in very complicated ways. But, you know, I should point out that training these recurrent neural networks can be very difficult and can be computational expensive. This is a case where, you know, you don't have very high powered computers. You try to run it on your laptop, you may be looking at weeks or months of computation time. So this is where you need to have some pretty significant computational power to work with. Here's an example of basically of a recurrent neural network. It's one of the inputs, then you have hidden units, you know, maybe one or more layers here going to output. But you'll see basically when I come to the point where I come at time t, and I put the time t inputs into the hidden unit, then basically you have this delay circuit out here. So that also, when time t inputs come in, you also put in what you put in the hidden units now with the state of the hidden units were at times t minus 1. So you actually have a feedback loop. So you have some, you know, memory of what happened in the previous set of inputs. This is basically just how it's unrolled in time. It's the same sort of models I just showed you on the previous. What you see once again here at time t, basically you input the things from, at time t, but also you input the state of the hidden layer at time t minus 1. Those are combined to actually give you the output from at time t. And then basically, here's just a few examples. There's extremely complicated architectures you can come up with. But here's one that just shows, for example, with 2 hidden layers, so it's deep learning, and it has basically a feedback from this node in the second hidden layer back to a node in the first hidden layer. But you can also have, you know, basically feedback that goes into the same hidden layer, things like that. So it can be very complicated how those are set up. And just here's another one you should be aware of is you can also have even in the hidden layer, the output layer, whatever the output layer puts out, it also could be fed back in to the hidden layer. You know, it could be, you know, this is just one hidden layer, but if you had multiple, you could feed it to multiple hidden layers. So there are many different possibilities in terms of the way you can set up these recurrent neural networks. Well, in terms of, you know, how do you test? You know, basically you divide in general your data set into training and test sets with no overlap between the sets. And then basically the test set is used to validate, your resulting model, the one you've trained up. And basically, you know, to make sure it didn't overfit, we're talking about overfitting, basically refers to the system is learning the specifics, the noise and the errors and all that in a data set rather than generalizing what the general trend is. So, you know, here's how you do it. Basically, you have a labeled data set. This is, you know, supervised learning divided into a training set and a test set, and there's no overlap. You actually then, you know, give the learning method, you expose that to the training set, you train it, and then you use that trained model, you expose it to the test set, data it's never seen before, to see how good or how accurate it is. Oops, sorry. And actually, instead of 2 sets, frequently if you have enough data, you divide it into 3 sets, a training set, a validation, and a test set. And the reason for the validation set is to help you avoid overfitting. So basically, once again, those are probably, you know, part of the problem with overfitting is that we're using a neural network, especially a deep learning network, generally have more changeable weights than you have variation in the data that you're trying to model. So that actually gives you a lot of possibilities for overfitting, where the method actually, when you're exposing it to the training set, it exposes it to, you know, things like noise in the training set and inaccuracies and stuff, which is not what you want. And here's a simple example here on the left. Basically, you see we have some data points, and this actually did a good job of fitting those points. It kind of goes up and it drops off. Whereas if you do overfitting, what you see is over here where it actually tries to run through every point. Even if there's some noise or inaccuracy, it tries to get every one of those. So this is basically, when you try to expose it then to other test data, it's not going to work as well with this model on the right as it does here where it's generalized on the model on the left. So that's why, if you can, you create a validation set. Basically, what you do is you start training the model using the training set. You stop the training at certain points. You check the error and the validation set to see if it starts going up. As long as the error for training and validation are both decreasing, that's great. Continue with training. But once it gets to the point where the validation set error starts to increase, that's where you need to stop training to avoid overfitting. And that's what you see here, basically. Here on the x-axis, when it says number of epochs, that's basically the number of training cycles. Here's the error. And you'll see here in the kind of the dark or the black line is the error as you train the model. And then in the kind of gray is the one if you use the validation set. And so, you know, as you train, you go down and periodically you stop and see how the validation set when you expose the system. And it keeps going down until here. You see right here at this break, training, you know, error for the training set keeps going down, but the error in the validation set is starting to going up. That means at this point, right here, time to stop training. That's where you should stop training, because at that point, your model is generalized the best it can, and any further training is going to start learning those, you know, inaccuracies and noise that you don't want it to learn. So basically what you do is you set it up, training set, you know, you can learn it, you use the validation set to stop the training. And then once again, you have the learn model, you run it against the test set to make sure you're okay. There's a few problems with the, well, actually several problems with anything, but we're going to talk about three particular problems with machine learning: bias, non-local minima, and the curse of dimensionality. Bias, basically what you have to do is when you're going to train a model, you need to train it on a data set that has the same characteristics as the population or the, you know, that you're going to use that model for. So for example, if I collected a data set from, say, a geriatric population, you could train a model, but then if I tried to apply it to pediatric population, to a bunch of kids, chances are it would not do very well. So that's the case, you would have bias in your training set. And something else to always remember is that your target population may drift over time. So you may at some point need to retrain the model if it drifts enough. Non-local minimum, basically, with machine learning, you define an error function. Basically, it tells you how well your model's doing. And the whole goal of machine learning is to change your parameters, say weights in a neural network, to minimize that error function. And so, the idea is you want to find what's called the global minimum, the lowest value of the error function, which is the best theoretical performance you can get from that model. But unfortunately, that doesn't always work. A lot of times what they'll do is they'll actually do something called the sum of squared errors, where you take the actual true value of for a patient minus whatever the output the system does. You square that, and then you sum that up. You add in overall the output nodes and all the different patients and stuff. Well, you'll see, since this is each one of them is squared, it's always a non-negative number. It's always 0 or positive. So, and then what you want to do is you want to basically adjust those weights in your neural network so that you can lower the value of that sum of squared errors. There's a number of different ways to do that, but generally the so-called gradient descent method is what it's done. And basically, if you do this in multiple dimensions, these are basically integrals. We're not going to work. For those that know calculus, this will probably make sense. For those that don't worry about it. I'll try to explain it more intuitively in the next slide. Basically, what it is here we have like a sum of squared errors with just a parameter 1 weight and stuff. And you see here W1 star, that's where you want to be. You want to basically change the weight so that weight is W1 star and it's the best performance. But suppose you were over here at W1R here on the right. Basically, what I've shown is basically this is what's known as essentially what the derivative is in calculus is the you may remember the slope of a line from high school. Basically, the derivative in calculus is a generalization of the concept of the slope of a line. You can find the slope, or basically how fast a curve is rising or falling at any given point on the curve using calculus, using derivatives. But unlike a true line where the slope always stays the same, it changes. You can see up here high on the right, basically it's going up very fast. When you get closer to W1 star, it's not going up as fast. And over here, it's basically now it has a slope, but it has a negative slope because basically it's decreasing here. So positive slope here, a negative slope here. And so what I want to do is, if I start out at W1R, is I want to change the weight so I get closer and closer to this minimum value. So I want to move to the left. Well, remember that this derivative is positive here. So if I take minus that derivative, I take the current weight minus this derivative, it's going to get me closer to that point that I'm interested in. And so, in gradient, even in multidimensional, always points in the direction of the maximum increase of the function. And then basically, so the negative always goes to maximum decrease. So basically, you want to update your weight somehow. You want to take whatever your current weight is, like W1R, you want to change it to a new weight by adding that current weight minus, or plus some change. But that plus, basically that changes, you want to make it minus the gradient. Minus the gradient. And this new is just a learning trait between 0 and 1. I won't talk about it, but basically, if you do the current weight minus the gradient, that gets you closer to the weight that basically minimizes the error. The problem is, in reality, is that, since you have multiple weights, you have, instead of, showing just a few minima like I've shown, you think, well, it's not that hard to find the global. But it will actually be, there can be, in a real life, when you have lots and lots and lots of weights and stuff, there could be thousands, tens of thousands, hundreds of thousands of these local minima and stuff. And frequently what's going to happen is you're going to wind up getting trapped in one of these local minima, like this blue little dot or ball did here. And that is actually going to basically, what you have to do then is decide, is that performance of the system at that point, is it good enough for your application or not? So basically, once again, frequently you wind up getting trapped in one of those local minima, and you have to see, are you doing well enough for whatever application you want? The other problem I want to talk about is the curse of dimensionality. It might seem intuitively to you, at least, that if the more variables I have for a given patient, say, the better off it would be. But that's actually not the case. In general, the curse of dimensionality refers to the point that, the more variables you add, probably the worse it's going to do. And essentially what it is that the model starts out, if it assumes all the variables you give it are of equal importance, but it turns out that in practice, some of them may be irrelevant, and that can lead to wrong classification known as curse of dimensionality. It's a simple example. Suppose, each patient is described by 20 variables, and only 2 of them are relevant for whatever classification you're interested in. Well, if it turns out that if you have a patient that has 2 identical, of those identical in those 2 important variables, so you think they should be the class the same, but if they're distant, have different variables for the other 18, and basically what's going to happen is frequently your model is going to give you a wrong classification. They're going to be assigned to different classifications. So basically the bottom line is you're basically dimensionality, that's the number of variables. Here's performance. So what you're going to find, if I have a data set with a given number of patients, there is some number of variables at which I get the maximum performance out of the system. It goes up as I increase the number of variables, then it starts going down. As I get more and more variables, I actually get worse and worse in my performance. And unfortunately, there's no way to theoretically say what that optimal number of dimensions is. So you have to kind of experiment and play around and see. So generally, the way you solve that is you get rid of some of the variables you have. And one of the ways that's a popular way is known by as principal components analysis. And all the principal component analysis does is it basically reduces the dimensionality of the number of variables. We have a large number of interrelated variables. Essentially, it retains as much of the information in the data set as it can by transforming to a new set of variables that are uncorrelated. And essentially what you do is you have multiple principal components. So essentially you pick out the first so many of those, keep those are where most of the information's at, and you throw away the rest of the variables. And then that basically helps you do better in terms of the curse of dimensionality. All right, so basically I just want to, I know that's a really, really fast presentation over that, but I want to at least cover a few examples of healthcare applications. And machine learning's been applied everywhere in healthcare. I've got a list here, which is certainly by no means exhaustive. So for example, medical diagnosis, you have patients that come in with a range of symptoms and stuff. And basically, it's a problem of pattern recognition. So you can train, for example, neural networks to help you do it. Interpretation of radiologic images. There was actually an article come out, or some news come out recently, I think, from England, where basically they found that they trained basically some sort of a machine learning system to interpret mammograms to look for cancer, and the system actually did better than the trained radiologist. Fraud detection, or you can look at patterns of care and claims and stuff to see if people are overbilling. Quality of care, or people actually getting the care they need in terms of current recommendations and stuff. Identifying possible drugs for diseases, characterizing microorganisms, to find out what properties they have. And then I just mentioned this last one, to predict seizures in epilepsy patients, not well-controlled medications, because that's what my research involves, and we're actually working with machine learning there. One thing you have to realize is when you're going to look on any machine learning, first question you ask before you ask, what sort of system I'm going to use, stuff like that, is what is the best data to answer whatever question you're interested in. So frequently you're going to be actually limited by the type of data you can get. We'll see that in a minute or two. But actually, from now on to the next few slides, I'm just going to consider the COVID-19 pandemic. For example, there's a product called InverVision used by China, and it actually looks at CT scan to detect lesions to see if it's coronavirus pneumonia or some other type. And they found that basically, if you have a radiologist read a CT scan, it's going to come up to 15 minutes to make that decision, whereas this product InverVision can do it in 10 seconds. Here, basically, I've shown you what a so-called transverse EC scan would look like. Essentially, here on the right is normal, person has no pneumonia. In the middle is a person who has flu pneumonia. And then here on the left is a person who has COVID-19 pneumonia. Just to get you oriented, basically, here at the top is actually the top patient. You can see the heart right here in this area. Down here's the spine. And you have to realize that when you're looking at CT scans, they're always set up so that you're looking from the feet. So what's on, what looks to be is on my left side, since I'm looking for the feet, is actually the right side of the patient. Well, here you can see for the COVID-19, you can see some kind of patchy infiltration. That's COVID-19, as opposed to over here that corresponds to flu. Well, here's basically what you do. Then you take the CT image, you pre-process it using something when it says HU, that stands for Hounsfield units. Hounsfield units are set so that basically air is minus 1,000, water is 0, bones are right around 1,500, 1,900, and then really heavy metals are 30,000. That's the range. So when you say pre-processing, what you do is instead of looking at that entire range, you cut it down to the area that you're interested in. Then you use a three-dimensional convolutional neural network to basically identify potential areas, and use another image classification neural network to actually classify each of those regions. And then that's actually found, gives you results in a probability of whether it's a COVID-19, flu, or normal. Here's just another more complicated vision of that. I'm not just going to talk about it. You see there's multiple layers, including convolutional layers and pooling and all that. So I know we're running a little bit late, so I want to get through. A few other things that machine learning can do is basically it might be able to help produce, estimate or predict seasonality. Historically, it's known that upper respiratory coronaviruses basically are bad in the winter and decline as summer comes around. But one problem you're going to have doing that in any of the work for using COVID-19 is that there's large areas geographically where you may have very little data, like sub-Saharan Africa, because of the limitations of their healthcare system. You may not be able to actually determine how many cases of COVID virus or COVID-19 there is. And also, unfortunately, political issues. I think I just saw a day or two ago that Brazil has taken off the information it has about COVID-19 patients in its country. So you could potentially use social media. People are saying on social media, oh, I feel terrible. I think I have COVID-19 and stuff. Well, as with any of that, there's been a lot published, but this sort of work's been done previously to track flu and other things. So there is a history of doing it. One of the problems with social media, though, is that it's in free text. So the same idea can be expressed in many different ways. So this means that you have to develop, use something called natural language processing to be able to interpret what those free text posts are. And natural language processing is another area of machine learning that's used extensively in healthcare applications. It basically breaks down language into shorter pieces and tries to see what it says. And deep learning has really been a major boon to the natural language processing community. Here's a simple diagram showing basically start here in the upper left with free text. You correct any spelling, part of speech tagging, like is it noun or verb or whatever, the concepts and all that. And basically you come up with some sort of more organized way of expressing what that statement said. And just a couple more slides here and then we'll wrap it up. Basically, there's a company, I think it's based in Canada, called Blue Dot that looks uses machine learning to look at infectious diseases. And back in 31 December last year, it warned its customers to avoid Wuhan, China. You may remember that Wuhan, China is where the COVID-19 pandemic originated. And that was actually before CDC and WHO. WHO didn't actually provide a warning until 9 January 2020. And this company, Blue Dot, also was able to predict what other Asian cities would have outbreaks based upon travel, itineraries and flight paths and that sort of information. There's another company called In Silico Medicine that uses machine learning technology. Basically, it looked essentially millions of different chemical compounds and identified, cut that down to a few thousand that might be potential medications. And it only took them, 4 days to do it. And then finally, there's the Chinese government is actually using an app that basically can estimate the probability that a person or neighborhood has been exposed to the virus, and is using things like locations from smartphones people are carrying, clinic information, own diagnosis, things of that nature. So that's, I know it's taken quite a long time. In summary, AI has a long history. Machine learning's the area that really is important, though. A large number of machine learning methods. We talked about KNearest neighbors, neural networks, and deep learning. Obviously testing is important to make sure your model works sufficiently for whatever your purpose is. We talked about a few potential problems: bias, non-local minima, and course dimensionality. And then basically, I'll give you a few examples. And machine learning holds great promise for healthcare applications. And with that, I want to thank you very much for your attention. If you have any questions, I'll try to answer them. And I've also given my contact information here. If you want to later think of a question or want to discuss any of this further, I'll be happy to talk to you. So thank you very much. Any questions?
Thank you. Wow, very comprehensive. Thank you, Dr.
Thank you.